We're going to cover this last section, 2.2 of normal distributions, in 3 days. So let's start with the first day of that. On this day, we're going to do 3 objectives. First one is we're going to use what's called the 68, 95, 99.7 rule to estimate the percent of observations from a normal distribution that fall in an interval that's either 1, 2, or 3 standard deviations from the mean. The second is use a standard normal distribution to calculate proportion of values in a specified interval. And then we are going to be using the table A, which is part of your formula sheet that's in the back of your note packet and the document I handed in class a few days ago, to find the percentile of the value from a normal distribution and the value corresponding to a certain percentile. Vocab words, we're going to be looking at normal curve, normal distribution, the 68, 95, 99.7 rule, standard normal distribution, and the standard normal table, which is, again, table A in your note packet. Now, as you start filling in your notes, two of our first vocab, the normal curves and normal distribution, is covered here. And let's just read this. One particularly important class of density curves are the normal curves. You have 2 of them down below. And normal curves are curves that describe normal distributions. A normal distribution is one that you're going to see the curve is perfectly symmetric, there's a single peak, and it's bell-shaped. So if you look at these 2 normal curves down here, they both have a normal distribution, is what you would say. What you're going to find in a normal curve is that the mean is right smack dab down the middle. And you're going to notice we're using mu. So this is the mean of the population. And we can move standard deviations. We can move an average amount away from the mean. That would be our standard deviation. This is stated in terms of sigma, and that is the standard deviation of the population. So when we're talking normal curves, we always talk about mu or sigma for referring to the population. So basically we're talking about mean and standard deviation. Now in the normal curve, if you wanted to know the actual equation for the standard normal curve, it is this function right here. You're not going to have to know this, but if you're loving calculus and you're a calculus geek, what you could actually do is take this curve, this function right here, and integrate it to find the area underneath the curve. What you're going to find, and this is what's incredibly important about a standard normal curves, is that the area underneath them is going to equal 1. It's 100%, or 1 as a whole, which makes it great for probability theory, for looking at proportions, and things of that nature. The height of the curve doesn't matter. It's always still going to be 1. The area of it is just going to adjust accordingly. If you were asked to describe the normal distribution, what they're asking you to do is to look at the normal density curve and look at the features in terms of the mean and standard deviation. As you see in the picture on the right, the mean is going to be at the center of this curve. So that actually gives it a special feature. When we draw a line straight down the middle of this curve, we're actually at the median and we're at the mean. And these 2 curves are perfectly symmetric. What we see on the right-hand side is just a mirror image of what we see on the left-hand side. It makes this perfect to do things with chance outcomes or probability, which we will later on in the year. We will also use it to make statistical inferences towards the end of the book. For now, we're going to use it to help us understand some real-life data. We're going to do many examples in the rest of this section. A lot of good examples deal with test scores. The ACT and the SAT tend to have a standard normal distribution, where what you're going to see is this unimodal peak here right in the middle. So most people are scoring at the mean. You're going to have some of those people doing much better on the high end or not as well on the low end. Once we know the mean, we're going to move a standard deviation. We may move 1 standard deviation. What you do is you move over 1 standard deviation and you just drop the line to see where you hit the curve. This right here is an area under the curve. We're going to be able to find the area under particular portions of this normal curve. You may see some shorthand abbreviations for it. It would look kind of like an ordered pair. It's going to be a capital N, and what you're first going to see is the first element represents the mean of our population, and the second is the standard deviation of the population. So you could actually draw a picture of that scenario. Keeping in mind that the area under the standard normal curve is 1, this is how we would start to end up using it. First thing we do is we just sketch ourselves this curve, and right in the middle, if we're talking about z-scores or deviations from the mean, this right here is our mean. So we're going to start at the mean, and then we're going to move 1 deviation. We're going to move 1 deviation to the right and 1 deviation to the left. And if our data has a normal distribution, we can use the normal curve. And what we know about being 1 deviation away is that 68% of the data sits in that area. Now, what if we move 2 standard deviations? Remember, the definition of standard deviation is on average how far we are from the mean. So if I'm 1 standard deviation, we already know it's 68%. If I'm 2, we're going to go from here to here, and we've just expanded it out. The rule says 2 standard deviations represents 95% of our data. And then the last one is if we go 3 standard deviations out and we look at the curve, the entire area under this curve is 99.7% of it. Now, this is a curve that technically is continuous, and its asymptote is the axis. So technically, we could never get 100% of the curve, but we're never really going to go beyond, 3.5 or so in terms of the curve. So in this class, we're going to capture most of this curve, up to 99.999%, but not quite get to 100. Now, this is a good example of how you would use a real-life scenario and apply this 68, 95, 99.7 rule. So as you're still on the first page of your notes, this might be, draw the picture for it. What you're going to have to do in your homework and on the exam is to sketch a standard normal curve, put the mean there, and actually do your tick marks. You're going to go 3 on one side and 3 on the other side that represent the various standard deviations. So if we look at this first graph or curve here that's been sketched, what we've done is we have this. We have the Iowa Basics exam given to the 7th graders in Gary, Indiana, and this is what they told us about it. They don't have to give us the words for it. We can look at this and say it's a normally distributed curve. The mean is 6.84 points with a standard deviation of 1.55. So what they've done is they came here and they plotted the mean. They then added 1.55 to get this number, and then subtracted 1.55 to get this. Now, to get the 2 standard deviations away, clearly they're going to take the mean and they're going to add to it 2 standard deviations. So times that by 2. And then do the same thing and subtract it by 2. And then 3 standard deviations, take the mean and add to it 3 standard deviations and also subtract. Now, what you're going to be asked to do is to take this curve and answer a question. Here might be our question, part B here. This middle graph represents what percent of the Iowa Basics vocabulary scores are less than 3.74 points. So what you would do is you're going to go find, and you're going to see here we have 3.74 points. And how you read this curve is everything back is the less than, right? So this green section here is the area of the curve that represents all of those students that did less than 3.74 points. We can actually find this number pretty easily. Because we've noticed that we've moved 2 standard deviations to the left, we know if we go 2 standard deviations to the right, that this red area is 95% of the curve. Well, if that's 95% of the curve, and we know the rest of the curve is 100%, how do we find that missing green portion? What they're doing here is they're taking 100% minus 95. We're left with 5%. But because you're going to notice this perfect symmetry in this curve, this right tail and this left tail are exactly the same, so you have to cut it in half. And you're going to find that the area that they want us to find is 2.5% of the scores. Now part C is another example. Here they want us to find what percent of the scores are between 5.29 and 9.94. Well, if you look at our curve, 5.29 was right here. So we're 1 standard deviation to the left of the mean. And 9.94 is actually 2 standard deviations to the right of the mean. So what they want us to find is this entire shaded region, the red and the green portion. So how would you find that? There's many ways to answer these questions, folks. What they're showing you here is this. They're saying they know if we look at just this red portion, 1 standard deviation is 68% of the scores. So they have that part. They need to get this other green portion. Well, if we were to go out to here and to here, that would represent 95%, the entire curve. So what you could do is take the 95%, subtract out the 68%, and then divide that by 2, and that'll give you the green portion. Adding those two together will give us the area under the curve, or the portion of students that had the scores in between these two scores here. Let me show you some examples. Here's the first one in our notes. It says, according to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. That can be written shorthand like that. Sketch this distribution, labeling the mean and the points 1, 2, and 3 standard deviations from the mean. If you were asked to do this, you would want to come in and draw your axes there. Try to get some nice symmetry. And we know that the mean is going to be right in the middle, so we're just going to label that. And then we're going to go 1 standard deviation, 2 standard deviations, and 3. And we'll go 1 backwards, 2, and 3. And we don't necessarily need to put the label of centimeters there. We will label the axes though. So if we do that, I'm going to take 149 plus 9. And if we continue to do this, you're going to get a curve that looks like this. Again, just so you can back into the number, how did I get this one? I took the mean of 149. I added to it 3 standard deviations. And conversely, I went over here and subtracted the 3 standard deviations. Okay, we're going to start right here for Major League Baseball players. In 2009, the mean of the 432 batting averages was .261, and the standard deviation was .034. Suppose that the distribution is exactly normal. Again, we need to have this be the case. We need to know that the distribution is exactly normal. If it's not, then we have to use a different distribution, which we're going to learn about later on in the course. So what they've told us is that we're using the mu and our standard deviation, or sigma, and they wrote it shorthand for us. Part A, sketch a normal density curve for this distribution of batting averages and label again 1, 2, and 3 standard deviations. This picture is already done for us. So now we're going to go the next step and answer a question with it. Part B wants to know what percent of the batting averages are above .329. Well, if we look at .329, it's right here. And that is exactly 2 standard deviations from the mean. Here's our mean, here's 1, there's 2. So if it helps you to solve this, you can come on in. We know this is 95% of the data. Therefore, because this graph curve has perfect symmetry, again, right smack down the middle, there's a mirror image of it. With a perfect symmetry, just subtract that from 100, we're left with 5%. And we're going to have to divvy that up between the tail they want us to find and the tail over here. So you divide it by 2, and you're going to have 2.5% of the batting averages are above .329. You are going to have to answer all of the questions in this section in context. So you just wouldn't say the answer is 2.5%. You need to put it in the context and actually state what you were finding. Continuing on, Part C, what percent of the batting averages are between .227 and .295? They want you to show your work. Folks, we're going to talk in the next lesson about the 4-step problem for this, the state, plan, do, and conclude. And the AP board is going to expect you to do that every time for this, and they have a pretty standard procedure. A big part of their procedure is they want the sketch of the picture, they want you to color it in, and then they want to see your work on how to solve it, and then your conclusion. This is kind of the plan portion. The do is just showing our work to solve it, and the conclusion is just telling us the answer. So it's not as lengthy as some of the other write-ups. Well, here's what we do though. Let's just sketch it again. Here's the sketch. Here is 1 standard deviation away was actually our 0.295. And then I want you to change this. This number should be a 0.193 is what we wanted it to be. So if you look at 0.193, you're going to notice it's 2 standard deviations away. So here we have to do a combination of being 1 standard deviation and being 2 standard deviations away. Let's maybe talk about a different method for doing it. There's many approaches. Here's one. Cutting this down the middle, we know that 2 standard deviations is 95% of the graph. Why don't we just take 95% of the graph, cut that in half, and if we cut it in half, we're going to get this portion right here. So we know the area to the left of the mean that they want us to find is 0.475. Now if we go 1 standard deviation away, from here to here, that's going to be 68%. We'll cut that in half so we get this other side. That's going to be the 34.34. We'll just add those two numbers together and we're going to get the answer is the 0.815. So when you put that in context, notice what they said here. They said 81.5% of batting averages are between 0.193 and 0.295. That is going to be expected of you to state your answers like this going forward. Now, I'm not going to talk about Part D here, just cross that off, but I do want you to realize this AP common mistake here. Students sometimes apply this rule to non-normal distributions. Notice here it says this works reasonably well only for approximately normal distributions. So we're going to learn later in this section how can you tell if a distribution is normal so you could actually use this rule. Because it's not normal, we cannot use this rule. I'm going to skip talking about this example. If you want some more practice on this, try it or see me for some help. Let's go on to the next topic for this lesson. Now, in normal standard distributions, we're not always just 1 deviation or 2 deviations from the mean. Sometimes it's 1.67 deviations, and we don't have the 68, 95, 99.7 rule to go back on. We're going to have to use our table A, and I'm going to show you how to do that. What you're going to have to do sometimes with your data is standardize it so you can use it in a normal curve. And to standardize your data, all you do is compute the z-score like we did in the first part of this chapter. Now, the thing with the z-score, by definition, it's how many standard deviations you are from the mean, which is exactly what we were just doing. When you do that, it assumes it's a normal distribution, the mu or the mean is 0, and the standard deviation or the sigma is 1. This is a perfect picture of what it would look like. But when we transform it, we're not just putting normal data here on this x-axis. This is actually a z-score that you're seeing. So I've moved on to page 13 in this current note packet talking about the standard normal distribution. Write down that you're going to have to make the z-score. And again, it's important to realize that the mu is 0 and the standard deviation is 1. What we're going to do is end up referring to table A, and this is a table that they're going to give you on the test, and it gives you the area under the curve at various standard deviations from the mean or various z-scores. This is a nice example of how it works. You know, it doesn't matter the number example or the data we're dealing with, as long as it's a normal distribution. We can assume it's a normal curve, and all normal curves are the same with mean of 0, standard deviation of 1. So what we do is we just standardize all of our data so we can use the normal curve. And for this case, assume we had some data and they already converted things to z-scores. Here's their question. they have right here, what's the proportion that the z-score is less than 0.81? So they're going to tick mark the mean is 0, and they're going to tick mark all 3 of the standard deviations. 1 deviation, 2, and 3. We'll just find this z-score, or find this how many deviations from the mean on the graph, which is right here. And the z is less than, so sketch in the picture, this is what they want. Turn to Table A in the back of your note packet, or in the handout I gave you the other day, and here's what you do. This first column right here in the bold is the tenths position, so you're looking for 0.8. This row here is the hundredths position, so you look for the 1. And then you just go and you match it up until you hit the number. The area under the curve here is 0.7910. Or you could say 79.10% of your curve has a z-score of less than 0.81. Now in the rest of these notes, I'm going to show you 3 examples of just how to use the Table A. Tomorrow in notes, we're going to put the problems in context and do some real-life scenarios that don't have just 1 or 2 standard deviations. So let's start with this one. We want to find the portion of observations in a normal distribution that were more than 1.53 standard deviations from the mean. So, well, you're going to sketch your curve. Here's our normal curve. Here's the mean of our standardized data of 0. And again, our tick marks, and they're going to carry it out to 4. They typically will not go out any further than 4 on a standard normal curve. 3 or 4 is normally what you see. So, find 1.53. They want to know where it's greater than. Here's how you'd write it shorthand. I want the portion of the z-score, which is greater than 1.53. Now, the one thing I will tell you, using the normal curve, you could say the z-score is greater than, or it's greater than or equal to. It doesn't matter either way. Typically, you see them just write the normal inequality without the equals to sign. The table is read either way. So what you do is you go to the table. You're going to find the 1.5 in the column and the 3 in the row. Here's the column, here's 1.5. You're going to go out to 0.03, which is right here, and you see where they meet up. And what this gives you is the area from that z-score or that deviation all the way back to the tail end. That's this area. So this is 0.9370. Therefore, just do your math to back into it. Do 1 minus that. So if it said show work, this is all the work you have to show. You're going to get 0.063, or 6.3% of the curve is represented above 1.53 standard deviations from the mean. You know, be cautious of this AP common mistake. It says here when students are doing normal calcs, they often report the area to the left of the boundary when they're asked for the area to the right. This is why they want you to do a sketch. If you sketch it, you're less likely to make an error. Be careful because the table always gives you the area from here all the way back. Before we go to that second example of the area under a curve, let's look at this. What if it's a combination of 2 things, 2 different z-scores? Find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. Again, your first thing is to just sketch the curve, put 0 at the mean, and tick mark your standard deviations, and then go in and sketch the picture for that. They want, on this one they're starting at 0.8, so they are saying that this is 0.81. They went to the table and got the area under the curve. The area under the curve for a z-score of 0.81 is 0.73910. So then they decided in this one to now go in and plot the negative 1.25. Now there's a second table A. If you look in the back of your packet, there's one with positive numbers and there's one with negative. If you look up the negatives, do the same thing. Do negative 1.2 and find the 5. You're going to see that this area here is represented by 0.1056. So then in looking at the picture, they realized they wanted to take this portion out. So how did they do it? They took this answer and they minus this answer to get the area under the curve. There's a variety of ways to do this. This is one method. Notice here they say, can you find the same proportion using a different approach? Absolutely. There's many different ways to do this. You just kind of have to let your eyes look at it and just go with what your brain first says and try it and back into it. Normally, I'll tell you, if there's something like this, there's 2 or 3 or 4 different ways to approach it and still get it right. Let me show you this example in the notes. Find the proportion of observations from the standard normal distribution that are between negative 0.58 and 1.79. So first thing I'm going to do is sketch the scenario. It's right here. And I do want to put in the values so I know what I'm dealing with. This is 1.79 and this is negative 0.58. Now I'm going to show you how I do this. It's a little different from what they did in the last example. Now again, when we start doing the state plan, do and conclude, here is my plan, and then I'm just going to do. What I'm going to do here though is put this. I'm trying to find the proportion such that my z-score, or my standard deviations from the mean, is between negative 0.58 and 1.79. Okay, so that's kind of the math notation for it. Now to find that, what I'm going to do is I go to the table and I start here. I look up 1.79 on the deviations, and I found that the area was 0.9633. So what I then did is I realized this here on over is half of the curve. So I subtracted 0.5 from that. And I'm left with 0.4633. So what I just found is this portion. Now I come in and I'm going to find this negative one. So when I go to the table and look up the negative, I'll do negative 0.58 and it gives me this value. And what it has for that is says this is 0.2810. Well, from here all the way back again is half the curve. So I'm going to take that value and subtract it from 0.5. When I do that, I get 0.2190, which then is the area of that portion. So I'm going to add those two numbers together, and what I'm going to get is it's 0.6823, and that's the work. Now I want to tell you about a calculator trick you can use to check your answer. You're going to have to show the appropriate work on how to back into this on the AP exam and in your homework and on tests and all of that. But here's how you can check it. In the calculator, if you do second vars and then go over to distribution, you're going to be looking for this. Look for, it says normal CDF. It just stands for the normal density function, and it's going to find the area for you. And what you do is you have to type in 4 different things. The first one is your lower bound. The second number is the upper bound. The third is the mu, or the mean you're using. And the fourth is the sigma, or standard deviation. So I can actually check this answer, by the way. Here's what I'm going to do. Type in normal CDF. In the parameters I would use, my lower bound is going to be a negative 0.58. My upper bound is 1.79. This is a standard normal curve, or it's using the z-score, so my mean is 0. My standard deviation is 1. If you enter and hit enter, you should get this as the answer. Okay, the last example I want to walk through is going backwards. It says here in a standard normal distribution, 20% of the observations are above what value? They want to know, what value am I talking about? So what they're stating here is that this is 20% of the curve that's in the white. 20% is above. So what we know is this. We would say that the proportion we want to find is such that the z-score, or our standard deviations from the mean, is greater than some value, which is right here, that's our c value, is equal to 0.20. Now we have to be cautious because this right here, when we read the table, is less than. So look at the picture. If you draw the picture every time, it's going to help. What we know, this white area is 0.2, therefore this blue open area has to be 0.8. And you just go backwards. You look for the area in the table. Now when you find 0.8, it's going to be somewhere in between these two. There is a clear option. We have not gotten to past 0.8, so we cannot choose this one. We have to choose 0.7995 as the closest. And just look backwards and see what the z-score is. So we do know the answer. We want to find the proportion that the z-score is greater than 0.84. The answer is going to be 0.2. And that's how you work backwards. These examples have definitely covered these objectives. Your assignment when we get to class tomorrow is you'll work on the book assignment, and then we're almost done with this section. Your next homework is to take notes on day 4.